Previous video, we talked a little bit about CMake, but in this video, we're going to talk about a completely different subject, and that is the debuggers. And as the name suggests, debuggers are sort of tools that you use to basically to find possible flaws or issues with your program. But not only you can use debuggers in that sense, but you can also use debuggers as a very powerful educational tool to basically gain knowledge on the C++ language itself, and also to basically see how your source code, how your instructions you give basically impacts the hardware, how your data structures are laid out into the memory, and stuff of that nature, basically. Or in general, you can say things which are happening behind the scenes, and you as a programmer, you won't be able to see them directly. But debuggers basically provide you a way to basically see everything very clearly and vividly. So things to notice is that I'm using Mac operating system. So this means that I need to use the native debugger on Mac operating system, which is LLDB. Of course, if you're using Linux operating system, you have more or less the same capabilities with GDB or the GNU debugger, but the equivalence ratio is not 100%. So not everything in GDB exists in LLDB. Another thing to notice is that I wanted to test LLDB with the program, Runge-Kutta program that we developed earlier or in previous videos. But I sort of changed my mind. I said, let's start with something very, very simple. And then gradually we add more complexities by, let's say, printing some stuff. And then we add some variables. And then we add some functions. And then we can take a look at custom or user-defined data structures and take a look at how they look like in LLDB and how you can manage this stuff, or how you can even work with LLDB even. So I don't want to make a theoretical discussion out of this. So without further ado, let's jump into some examples. So I haven't done any magic, so I'm currently at the same sort of project directory. I just made a test directory, and it's empty, and I want to make a test.cpp, of course. Let's add iostream. And let's write the simplest program that we basically have in any programming language. And we return 0, and I save it. So things to notice, you need to add -g flag. This basically enables those debugging information. And I explicitly want to say -0 to turn optimization off, and then test.cpp. Take a look at this. Not only I have my executable, I also have a very strange looking directory. Let's take a look at it. I have a info list. Looks strange. I have resources, dwarf, and then I have another a.out. It's also another binary. So it turns out that this is the way it works. So this the second a.out contains all the debugging information of my test.cpp, and it is separated from the main executable. This is a better management of this stuff, and the source file, the sort of size file of my executable is going to be also smaller. So the way I fire up LLDB is that I say LLDB.out. So now it says target create, and then this is the address in my hard drive, and it has the architecture of ARM64, a.out. So the first thing I need to do is I need to set some breakpoints. Of course, I don't remember which line number I had in my test.cpp. So I can set it by the function name, basically. The way I do it is breakpoint set -name and main. So now this is my breakpoint. This is the address of that executable in the memory, which holds the instructions of the main function, which corresponds to line number 5 at test.cpp. And I can list my breakpoints by saying breakpoint list. Right now I only have one. And if I say run, then you can see I have a process 8014. It is launched at this location, the whole location, and it is stopped all of a sudden. And the reason for stop is it hits the breakpoint. And where it hits it at main, which is basically what we wanted to do. And this is the memory location of the instruction. It corresponds to the same one we had earlier. It corresponds to line number 5 of test.cpp. And it is, we are currently at frame number 0. And it is also beautifully shown here with this arrow that we are currently about to execute this line of code. We haven't executed it, we are about to execute. Before doing anything in LLDB, let's hop out from LLDB. You can press Control, you can see that LLDB is gone, now it's bash. You can press Control Z to get out. If you see jobs, I still have that there. Let's take a look at my processes. And I'm interested in A.out. Take a look at this. This is from grep. You can ignore this. So I have one process, AT14, which corresponds to this process, which we saw in LLDB. This is the executable itself. And I have another process ID, AT11, which corresponds to LLDB A.out. So this is how LLDB basically works. Whenever you say run right here, so LLDB starts a new process with a fresh process ID, in this case AT14, and then LLDB has control over that process in the way that you can manipulate and inspect your basically executable. Okay, now we come back to our LLDB again, and we can say process status, and we get the same amount of information that we got in the beginning. By the way, if you don't like typing the whole word like process status like this, what you can do, LLDB supports also aliases. So you can say command the way you do it, alias, and then PS process status. So now I am using PS as an alias to say process status. So if I say PS and then hit the return key, I get the same information. Okay, at this point, what can I do? We are at the debugger, we have this line of code, and the first thing with this hello world we can do is to take a look at our register. We say register read, this is all my register, it says general purpose registers. So these registers are basically the things that your CPU have access to basically do other, like different stuff, like it can be address management, memory management, or data storage, or things of that nature. The first thing which basically catches my eye is this hello world. I haven't executed this line of code, but I already know that my X1 register holds this constant string. By the way, this thing right here is the memory address of my X1 register, and it's written in the form of a hexadecimal format. So 0x in the beginning shows it's in hexadecimal format. So one capability that you have in LLDB is that you can inspect your memory basically the way you want it to do. So if I say memory read, and then I give this address, I copy this address, I paste it right there, and then you can see a strange looking sort of print statement right there. So this is the memory address, corresponds to this one, and then we have some numbers, and then we have hello world right there. So this thing on the right is the ASCII representation of whatever you see on the left. And whatever you see on the left, each of these sort of pair of numbers, or it can be number character or whatever, these are written in hexadecimal format. So if you Google, for example, if you Google ASCII table for in hexadecimal, then you can see, for example, symbols like A, B, C, D. They all have a corresponding value in hexadecimal format. So 48 is the corresponding hexadecimal sort of value of capital H. And the same way, 65, same way 6C, and then always written as 6F. And every sort of this pair corresponds to 1 byte in your memory. So this means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 bytes here. I can show this also in a better format. I can say memory, read, I can format my data as characters, and I can say my size is 1 byte, and the count is 13. I want to see only 13 bytes. And this is the starting location of my memory address. And if I do that, I only see my hello world. If I do 14 here, I see this null terminator. And this is this basically triggers that memory that in C style, you know, when you are having a char star or a, let's say, character array to show a constant string, then it has to be always null terminated. This is exactly the same thing, right? So this is the first thing you learned. What else can I do? I can manipulate stuff here. I can trick. So if I say right now continue, my program is going to continue. Or in short, I can also say C. If I hit the return key, now you see that in terminal, I see hello world printed. If I run my program again, right at this line, if I say register read and then x1, I can see this is my memory address at x1. And it holds also this sort of constant string right there. But I can manipulate the memory address at x1. I can say memory, not read, but write instead. And then I can, so these things were written in hexadecimal format. I need to also write it in hexadecimal format. For example, I can use 48 to print, for example, 3 capital H. The way I do it is 0x to show that it's hexadecimal, and then 48, 0x, 48, 0x, 48. And then I don't forget to put that null terminator, that is 0x, 00. If I hit the return key, now I can prove you that I have manipulated the memory address at x1 register. I say memory read, format, character, size of 1 byte, count of 3, because we have 3 letters or 3 bytes. And then the memory address is here. Voila, you have 3 capital H. If you go with 4 characters right here, you see your null terminator. And if you continue to go 13, you see the rest of hello world. So I have manipulated the memory at this location. So this means if I continue my program, when cout sees this null terminator, it's going to stop printing. So I should see only 3H printed instead of the whole thing printed into the terminal. So if I hit the return key, you see that this 3H, capital H, is printed. So isn't that cool? So let's add some more complex stuff in our test.cpp. I quit. There, let's add, let's say, a variable I of type int and assign a value of 5. Let's compile this and let's fire up LLDB, and then let's set our break. Oh, by the way, you can say BR as short for breakpoint, S as short for set, and -N for name, and then you can say main. It's the same. If I say run, now I have a variable here. How can I see this variable? I can say frame variable. It's of type int. It has, oh, this strange value. Now, this is your second lesson. You kind of understand the value of initialization in C++, because we always say that when you sort of define a variable, you have to initialize it because you might be use it by mistake, and then whatever you access there, it might be any garbage in that location in the memory. So I can say frame variable &i to get the address of this variable, which is of type int star, of course, it's the address. And I can say memory read format of decimal, because it's an integer. And then I can say size 4 bytes. I know my integers are 4 bytes. I'm going to show you in a second. And then I count for 1 because I have only one integer, and I'm going to give you this address. Then if I do that, then I see it's the same value of my variable right now. So if I use I in any expression, it has this garbage value. So now you understand basically the value of initialization in C++. You always need to initialize your variables. Yeah, so now if I say next, then this line of instruction is going to get executed and my I is going to get basically the value of 5. I can also say, alternatively, I can use only n. I say n. Now we are at line number 6. It also shows it right there. And you can see that frame variable I equals 5 right now. By the way, if you want to have information about your current frame, you can say also frame info. It exactly prints this line of data which you have in process status, like in PS. It shows the same thing that you had in the beginning when you run stuff. PS doesn't work right now because it says it's not a valid command because I quit from LLDB and then I came back. So if you use an alias, then the effects are temporary. If you want to have them permanently, you need to put them in a file at your home directory. I think at something like init LLDB. So there has to be a file like init LLDB, and then you need to define your stuff right there. So I can do this with process status right now. There we go. So this is the same information if you say frame info. What else can I do? As I said, if I say frame variable and then I say ampersand I know that I have this thing, and then I can print the value of I. Right now it's 5, but I can manipulate this address of memory as well. I can say memory, right at that address of memory, I want to, for example, put 3 in there. 1, 2, 3, 4, 5, 6, 7, and then I say 3. And now if I say print I, take a look at this. Of course, I could also achieve the same thing by writing expressions. So LLDB also supports expressions. The way you do it is like you say expression in whole word or whole world. No whole world, in whole word. Like you can say expression or you can say expr. And then you can type, for example, I equals, I don't know, 10. And then you print your I. Print I. Then you're going to get your 10. So this is very simple. So we have seen some stuff. We can make it more complicated. We can add also a function and see how it works. Let's quit LLDB, go back to test.cpp. And then I can add a function right there, print function, for example. It's going to be very simple, a const int reference of v1, for example, and int, for example. Let's see the value of sending stuff by reference and sending stuff by copying them. And v1 and v2. And we just want to print them out. And of course, I need to use my function. And then I say G++, and then I fire up my LLDB. Breakpoint set name main. Then I run my function or run my program. Then it stops here. I say next. Right now the instruction is at line number 13. We are about to execute it. If I say n or next, it's going to step over this function without going into that function. But I want to do is I use s to step into this function. Now you can see that my memory address is different from the main function. So we jumped into another location in memory. So now you can see this with your own eyes that what it means to call a function in C++. We are literally jumping into another location in the memory, which corresponds to the instructions for print. Take a look at this, v1 and v2, how they are represented right there. v1 equals to this thing, and v2 equals to 5. But this thing is, it was a constant reference, right? It looks familiar. It's a memory address of... it's a memory location address, but it looks familiar. We have seen this. If I say frame variable right now, I only have access to v1 and v2. I cannot see my I anymore. So there you go. you congratulations, basically. You also learned that what scope means in C++. You only have access to v1 and v2 right now. If I say backtrace, or if I say thread backtrace, then it's going to give me the call stack for my function calls. Take a look at this. Here's my main, frame number 1, and here is my print function, frame number 0, and this is star, shows me the current frame that I'm already looking at. Frame number 2 is the dynamic linker, which is responsible to basically load my the executable and then try to run the main function. We're not going to mess up with this one. But if I switch my frame to frame number 1, I will be able to see the variable I. The way I do it is I say frame select 1. Now I'm at main function, and I can say frame variable, and then I see only I. Now I don't see v1 and v2 anymore. And as I say, congratulations, you learned what scope means in C++. So now I say frame, one thing before I forget, if I say frame variable ampersand I, take a look at this address and take a look at v1, these two addresses of memory. They're the same, right? So that's the value of basically sending stuff by reference. Congratulations, another lesson in C++. Now you can see these things basically so clearly by using a sort of a debugger, a tool like LLDB. So now if I say frame select and I go to my frame number 0, which was that function, I can say, for example, print v1. It prints me the value of 5. But what do I see here? I see a memory location right there. Let's inspect this v1. If I say frame variable and then I say ampersand v1, is it going to be the same as this? You might think, right? Let's take a look at it. It's not. These two things are completely different, right? So this is a memory address which contains the value of the pointer, or which is another address which points to variable I, which has the value of 5. I can prove it to you. If I inspect this memory location, I can see exactly this thing written in there. But first I need to know, because I is an integer, I need to know the size of int star. I say expression size of, and then I can say int star, it's 8 bytes. So now I can easily say memory read format hexadecimal, that's x, and then you say size 8 bytes, and then count is 1. And what is my memory address for v1? It's that right there. If I hit the return key, there we go. This is exactly the same address that is inside v1, which is basically pointing to a variable I, which has the value of 5. Isn't that beautiful? Now you basically literally gain insight of how things are managed in your program. What else can I do? So this v1 currently is in my stack, so I can also prove that. Take a look at this. It is like the last 4 things is EC38. So if I take a look at my register, my stack pointer, it starts at EC20. Now I can say memory read at EC20. It gives me this thing, but I can also interpret it into another format. So I can say format hexadecimal with a size of 8 bytes and with a count of, I don't know how many, but let's say like 6 of them. And let's do this. So now this is the top of my stack, not this one, not that one, not this one. This seems familiar, right? This is the address of, this is the content, and this is the address. So 30, each of these is 8 bytes. So this is going to be 38. So this is going to be 30. The first element is 30, and the second one is going to be 38. So 38 is v1, is the location of v1. So currently V1 sits on top of my stack right now. So congratulations, you're learning like you're gaining insight and more stuff about your C++ application right now, right? So of course I can say next, then I can go to the next line, and oh, take a look at this. If I say expression v1 equals 4, does it gonna basically work? Or let's see. If I do that, if I hit the return key, it says cannot assign to variable v1 because we have the const qualified. Because it's a const int ampersand, right? It's a const sort of reference, const int reference. So I can't assign any variable, but I do have access to the memory. So I can say memory, write, and then I can give the address. Then I can use, for example, 1, 2, 3, 4, 5, 6, 7. And then, I don't know, I can put 2, for example. And I can print my v1. Up, print v1. Now it has the value of 2. So there we go. Now if I say, again, process status, I see I'm right in the second line. And v2 also the same. v2 is somewhere also on my stack, most probably. But if let's just go back to our main function. And this is, we already have seen that what's happens here. And so now what I can do is to add another complexity level. I can see how like custom data structures are looking like into GDB. How can I inspect them? Let's quit LLDB. I say yes. Let's go out test.cpp. I want to define a, I can of course define my own class, but I want to use the stud vector for that to make it easier. So I call it v, and then I want to initialize it with 1, 2, and 3, let's say. If I do that, of course I need to, before I forget it, I need to add a vector as well. And I say G++, it gives me this error. Oh, of course, the initializer list is part of the C++ 11. Should work. Yeah, and now if I fire up my LLDB and then I set my breakpoint, and I can run my program. By the way, one more thing that I forgot to tell you that is you can also write expressions. For example, I do have access to my print function. I can say expression. What does print do? It just prints 2 values that you feed it. So you can say print, and then you can say 10 and, I don't know, 34. And then you hit the return key, and then you basically get the output. So you can also inspect your functions with LLDB without even going there when the instruction goes there. But right now, if I say frame variable, take a look at this. I have my integer, and then I have my vector, which is of type std vector. And then the size is 3. And then I have the values. The first element is 1, the second element 2, third element is 3. And you know that in C++ indexes start with 0, of course. And now let's take a look at our custom data structure, which is this stud vector. If I say xpr, expression, and I say size of a v, this is going to be the size of my vector. So the size is 24 bytes. So you might think that if I interpret the memory location of starting v, where v basically starts in the memory, and then I interpret it because it's an integer, it contains integer values. If I interpret it by 4 bytes, probably I will be able to see 1, 2, and 3, which are the data members that I have. So let's do that. If I say frame variable ampersand v, it's going to give me the address. And now if so I know the address, and I know that the size is 24 bytes. I can say memory, memory read format. I know it's decimal because it's integers. Size is going to be 4 bytes. And because that's my integer on my machine. And count is going to be 6 of them, because 6 times 4 is 24, and 24 equals to the whole size of this V. And now I give the memory address of V. If I hit the return key, wow, I see garbage. So how does this custom data structure work? I can't see my data in there. Let's take a look. If I say, I can cheat. I can say frame variable v0. It's going to show me the 0 variable, the first element. And if I say ampersand, it's going to give me the memory location. Take a look at this memory location. Take a look at this memory location of v. Wow, it's completely different. So my object v has this memory address, but the data that it basically has is somewhere deep in my memory. How does that thing work? So it turns out that this is how basically the vector class is implemented. If I say expression v dot underscore underscore begin and then underscore, this is going to give me the pointer to the first element that I have in my vector. If I hit the return key, you can see it's a pointer and it points to my first element. And I can prove you that the data in my vector are in consecutive memory sort of locations, because if I say frame variable v0, I get this address. If I say the second element, it's going to be 4 bytes distant from this one. And if I say the second one, it's gonna be again 4 bytes distant from this one. But pay attention to this one. This is the starting memory sort of address for the first element. If I say expression and then I say v dot pushback, and then I add value of 10, for example, in my vector. If I hit the return key and I print my v, I can see that I have 10 right in there. But if I say expression v dot begin, take a look at this. Is that the same as, where is it, here? No, it's not. And why is that? The reason for that is behind this, we're using pushback. So when you use pushback and sort of dynamically try to add more and more elements into your vector, each time you do that, so vector class goes somewhere into the memory and tries to find at least, so you have 4 elements, at least 4 elements, consecutive chunks in the memory, which they have the capacity of 4 bytes to hold an integer, enough to hold an integer, and then it reallocates the memory, it seems, because we started with a different address, and after we used pushback, we ended up with another address. And another thing we also notice about vector class is that it manages its own data structures with a pointer. So right now, if you remember, my v had the size of the object v had the size of 24 bytes, right? Right here, I said the XPR size of v was 24 bytes. I pushed back another element into it. Now, is the size different? No, it's not. The same object has the same size. I can also prove it to you. I can say EXPR size of v. You see? I can push another basically element and the size is not gonna change. That's how basically std vector or standard vector works. It manages its data structure with a pointer which points to those data structures in contiguous memory block. I literally proved it to you by this example. But each time you dynamically sort of push something into the element, then it's going to reallocate the memory, and the starting address is going to change each time you do that, which is, of course, not a good thing due to performance issues. You don't want to reallocate stuff. So there we go. I think we played enough with LLDB today. And as a summary, you saw that how you can get information from frame, how you can basically read your stack pointer, read your registers, and then how you can manipulate the memory addresses directly. And you saw the value of sort of sending stuff by reference, sending stuff by copying, and you also saw, for example, the value of scope, how in each frames we had basically access to different variables. And then finally, you saw that how basically you can inspect custom data structures. Of course, I haven't defined my own class, but I use a StudVector. And then we, for example, we were sort of shocked that why our vector object has a size of 24 bytes and the data members are not even shown. When we inspect the memory at those locations, we don't see 1, 2, and 3 there. And then later we realized that, oh, this class basically manages stuff with a pointer, and then it points to another location in the memory, and we literally also take a look at those memory addresses. So this was also a short summary, and I think that's enough for today, and I hope you learned something from this video as well.